Welcome back to the great adventure, Pediatric Pulmonary Physiology. This is the sixth presentation in the series, and we're going to deal with pulmonary mechanics, part one. So this is the great adventure, Pediatric Pulmonary Physiology. And as you can see, we're the sixth presentation here, just beginning a three-presentation series. And just to remind you, the summation of the last several presentations dealt with gas exchange. And the key issue there was that P alveolar O2 and P alveolar CO2 are determined by VQ. Normal situation of VQ of 1, which gives us a P alveolar O2 of 100, P CO2 of 40. VQ, there are only two abnormalities in VQ. VQ greater than 1, which is a increased PO2 over normal and a decreased PCO2 below normal, and decreased VQ, less than 1, which is a decreased PO2 from normal and an increased PCO2 from normal. What determines these differences in VQ throughout the lung? That's really the subject of pulmonary mechanics. So we're going to be talking about an introduction to pulmonary mechanics and pulmonary compliance, two fairly large sections today. So introduction. The distribution of ventilation is really determined, that is within the lung, regional differences in distribution of ventilation are really only determined by two things. Either areas of lung where there's decreased sensibility, and you can see that if you have some degree of stiff lung compared to relatively normal lung, when you take a breath, most air is going to go here, less air is going to go here. And airway obstruction. So again, if we have a narrow airway, when you take a breath, most air is going to go here, with a less amount of air going here. So let's just review what happens when you take a breath from a physiologic point of view. So your diaphragm contracts, and we'll go into much more detail about ventilatory muscle function down the road. But basically, you decrease intrathoracic pressure. That is, you make it more negative. Okay. What this does is it stretches the lung, so alveolar pressure also decreases. So you now have a tube where you have unequal pressure on each side of the tube, so flow occurs. In this case, flow goes into the lungs, and therefore volume increases. Right, and then that's the end of inspiration. For exhalation, you simply relax, and what happens is that intrafloor pressure goes back up. This initially compresses alveoli, but it causes flow outward, and volume returns to normal. So that's basically a respiratory cycle. There are two major issues with respect to pulmonary mechanics. One is compliance, and compliance equals change in volume over change in pressure. The other is resistance. Resistance across a tube, for example. This is the change in pressure at both ends of the tube divided by the flow that's achieved. So how do we measure these? So pressure is really fundamental. And pressure is measured in what's called a differential pressure transducer. So you have a connection here and a little area here or volume in here. It's separated by a membrane which has an electrical circuit in it. And that electrical circuit basically quantitates the deformation of this membrane. So if P1 is larger than P2, this is going to be deformed in this direction, and the electronic circuitry is going to pick that up, and that is going to be proportional to the difference in pressure across that membrane. This is referred to as the pressure walk, made popular by two of my friends, Jules Allen and Howie Panich from Children's Hospital of Philadelphia, among others. And so basically we have pressure at the mouth, pressure in the alveolus, pressure in the intrapleural space, and barometric pressure. What we're measuring is what's between the pressures. So between the mouth and the alveolus is the airway. So anything that uses mouth pressure minus alveolar pressure is a measure of airway, compliance, resistance, whatever. What's between the alveolus and the pleural space is the lung, and this is called transpulmonary pressure. So anything that measures alveolar minus pleural pressure, or often mouth minus pleural, and you'll see in a moment how we do that, is the lung. Pleural pressure to barometric pressure, what's between the pleura and the outside is the chest wall. So whatever measures pleural pressure referable to barometric pressure is measuring chest wall compliance or whatever. Between mouth pressure and barometric pressure, we're measuring the entire respiratory system. In the intensive care unit, for example, we often look at mouth pressure um, against barometric pressure as a measure of total respiratory system compliance when we're looking at children on a ventilator, for example. So if we want to measure alveolar pressure, okay, we use an intraesophageal balloon. Absolute intraesophageal pressure is slightly positive compared to pleural pressure. However, an esophageal balloon reflects changes in pleural pressure better than any other technique. A technique that has been used is to create a mini pneumothorax just under a place where you can put a small catheter in. So that does measure interpleural pressure, but it unfortunately does not reflect changes. So we use an intraesophageal balloon, and this is positioned in the mid to lower esophagus. So basically, it's a catheter, again, connected up here to a differential pressure transducer. The balloon around this is primarily to prevent mucus or other things from getting into these little holes and plugging them up. So this balloon is just to keep this clear so that it accurately measures pressure. And this is a very thin, usually latex balloon. This is an example of some balloons. Historically, they were often homemade, and they're actually made with a condom here, so that's how thin this material is. But this, again, is connected to a catheter so that one can measure the pressure in here. In this case, we're using it to measure transdiaphragmatic pressure, but you can see we have two balloons in this case. The balloon primarily serves to prevent mucus occlusion in catheter holes. We don't want to inflate the balloon so much that air causes a positive pressure. Usually it's only about half an ml for the average size esophageal balloon. This is work by Carolyn Beardsmore many years ago, who wrote a classic article on how to measure interpleural pressure accurately. And what is shown here, okay, is actual change in pressure. This is the change in volume of the balloon, all right? And you can see that a thick balloon is not going to reflect changes very accurately. A thin balloon really is what you want. The other thing is that you don't want to overfill or underfill the balloon. So a balloon that's overfilled basically means that because you're putting the balloon in a negative pressure relative in the esophagus, it's going to dilate and damp your signal, all right? And as you can see here, with a overfilled balloon, when you put it in the chest, it does not measure pressure accurately as it should. An underfilled balloon is going to have problems with positive pressure because in this particular case, you're not going to be able to keep the balloon open off of those holes, and it's not going to measure the pressure accurately. Positioning the balloon, so we have a subject swallow the balloon in the stomach. So in the stomach during inspiration, the pressure will be positive. So you pull this back gradually until the pressure during inspiration becomes negative, all right? And so basically you're doing this. Here with the balloon in the stomach, when the person takes a breath, the diaphragm increases intra-abdominal pressure, and this will be a positive pressure. When you pull it back up into the esophagus, mid-esophagus, then inspiration is associated with a negative pressure, which will be reflected as negative pressures. All right, so basically we just said that. Flow. So resistance, recall, equals change in pressure over flow, change in pressure across a tube, for example. We can reconfigure this equation so that flow equals change in pressure over resistance. So if we have a constant resistance, we can measure the pressure difference across it, and that is flow. And in fact, we have a device that does that called a pneumotac. So here we have flow going in this direction. We measure pressure 1, pressure 2, and we have a fixed resistance in here, okay? So the flow is going to be this difference in pressure divided by the resistance, which we know because it's a constant. With computers, volume essentially equals the integral or integration of flow. So before computers, we used spirometers and exhaled gas collection, but fortunately now, we don't need to do that. So the way that we calibrate pulmonary function systems nowadays, using that use computers and pneumotachs, is that we have a finely calibrated 3-liter syringe, as shown here, and we connect that to our system. And basically, if we put 3 liters in here, this pneumotach is going to measure flow. The computer will integrate that, and so it should read also 3 liters. So that's really the way that flow is calibrated, and generally in pulmonary function systems, this is done daily. Spirometers, these are older devices that were once used to measure lung volumes. And basically what happens is a person inhales or exhales into this. There is water around this that kind of seals things inside this uh, tube here, if you will. If you blow into it, it will go up. If you inhale from it, it will go down. And because this pulley is going the opposite direction, inhalation will be up. So this is how this works. Person breathes in, water filled, he breathes in, it goes up. And you can see that with the pulley system, that actually comes down. That's exhalation. If he inhales, this comes down and then that goes up. So that's how a spirometer, classic spirometer, works. And we get a spirogram from that, which is time here versus volume. So this would be somebody breathing along, taking in a deep inspiration all the way in, blowing out forcefully. And you can see you get some flow here, and then returning to normal breathing. If we wanted to measure gas exchange or certain amounts of gas, in the days before computers, we had to basically collect exhaled gas. Now that really meant that you couldn't collect gas over short periods of time. The standard usually was a 3-minute gas collection, and then you measure that entire volume, divide by 3 to get the minute ventilation. And again, they're breathing through a one-way valve here, breathing in and then breathing out. You can see this being used during an exercise stress test, for example. There was a device called a TISO spirometer. This is a 100-liter spirometer. And again, this could be used to collect exhaled gas as well, as was done, for example, in this exercise study. All right, let's look at the 2 important pulmonary mechanics properties. And today we're just going to discuss compliance. Next time we will discuss airway resistance. So pulmonary compliance. Compliance, remember, equals change in volume over change in pressure. Now, you determine what you're measuring compliance of by what pressure you're using. Alveolar minus pleural, remember that's transpulmonary pressure, that's going to give you pulmonary compliance. Barometric minus pleural is going to give you chest wall compliance because what's between the air outside and the pleural space is the chest wall. And total respiratory system compliance is going to be barometric minus mouth pressure. This is what we commonly use in the ICU for a patient on a ventilator, for example. So if we want to measure lung compliance, it's going to be alveolar minus pleural, okay, for lung compliance. Chest wall compliance, barometric minus pleural, because what's between these is the chest wall. And respiratory system, as mentioned, as in the ICU. For more than one compliance in series, okay, that's one after the other. So if you want to measure, for example, lung compliance and chest wall compliance, right, both of these work together, all right? So the reciprocal of compliance is additive, right? The reciprocal of compliance is additive. Respiratory system, 1 over respiratory system compliance would equal 1 over pulmonary compliance plus 1 over chest wall compliance. For more than one compliance in parallel, compliances are additive. So if I wanted to measure pulmonary compliance, for example, I could measure compliance of the right lung plus compliance of the left lung to get total lung compliance. All right. In parallel, they're additive. In series, reciprocals are additive. Let's talk about 3 aspects of pulmonary compliance. Elasticity. So this is elastic tissue. It deals with structural components of the lung. Surface tension, probably the most important determinant of compliance, and pulmonary interdependence, which is geometry of the terminal space. So elastance. Elastance is a physics term that's used to measure strain over stretch, excuse me. In the lung, that would be pressure divided by volume. We do talk about pulmonary elastic recoil sometimes, so it's worth knowing this. But in general, people are more concerned with the distensibility of the lung, how easy it is to inflate the lung, and that's going to be change in volume over change in pressure. And compliance is the reciprocal of elastance. All right, so let's look at Hooke's law. All right, so Hooke's law here, let's say we have a spring, right, and we put a weight on that spring, so we stretch it. All right, we put more weight, we stretch it more. We put more weight, we stretch it more. Hopefully in the lungs we don't do this. All right, we can plot the force or weight that we put on the spring in this axis and the distance, okay, or volume. So here there was no weight, no stretch. Here we put a little bit of weight on, we stretch it a little bit more weight, stretch a little bit more weight, stretch it more. This is Hooke's law, and it talks about elasticity in the lungs. Now, it turns out in the lungs, every structure in the lungs is connected to every other structure by elastic tissue, which can be viewed as strings or rubber bands. Okay, so if we increase lung volume, we're going to increase the stretch on these springs, which is going to increase the size of all of these structures. Now, this really is an important concept because how do you design an organ where when you take a breath, every single structure inside increases to the same extent that the whole organ increases. The way we do it is by elastic tissue really throughout the lung so that every structure in the lung is connected to every other structure by elastic tissue. Okay? Increase in lung volume, increased stretch on these springs, increased size of all of these structures, alveolus, airway, blood vessel, lymphatic, all of them. And again, we're going to be primarily interested in pulmonary compliance, so we want to measure alveolar minus pleural pressure because what's between the alveolus and the pleura is in fact lung tissue. So this is transpulmonary pressure, PTP, and it equals alveolar minus pleural. So the minus negative value of pleural pressure is a negative, so a negative times a negative is positive. So by convention, as we draw more pressure to inflate the lungs, transpulmonary pressure becomes positive. And I think you can see here alveolar pressure, okay, versus pleural pressure. What's between these two is lung tissue. That's why it's called transpulmonary. Now, we obviously can't get a catheter into the alveolus to measure this, but if you have no flow, then the pressure at each end of a tube is equal. So in this case, mouth pressure minus pleural pressure gives us basically transpulmonary pressure. And this is what a so-called pressure volume curve looks like. As we increase transpulmonary pressure, we get increased volume. Note that the inspiratory limb is not identical to the expiratory limb. There is a space here, which we're going to talk about in just a few minutes about what that means and why that's the case. But basically, compliance is the slope of this line. So compliance of the lung is change in volume over change in pressure. It's the slope of this line. Now, when we measure transpulmonary pressure, we actually have to overcome two components. We have to overcome elastic tissue. That is, we have to stretch the lung to open it up, and that's overcoming elastic tissue, this elastic components of the lung. And we also have to overcome resistance. That is, the pressure we need to generate airflow, right? So transpulmonary pressure consists of both of these, okay? Now, can we measure this, okay? So remember, compliance, all right, equals change in volume over change in pressure. So we can reconfigure and we can calculate the pressure required to overcome elastance or volume as volume divided by compliance. Similarly, we know that resistance equals pressure difference across the tube over flow. So we can recombine here that pressure to overcome resistance equals resistance times flow. And so the elastic component is here, the resistance component is here. This is called the equation of motion of the lung. And it says that transpulmonary pressure equals volume divided by compliance plus flow times resistance. And we're going to be talking more about the significance of this equation in determining your pattern of breathing, for example. So compliance is volume divided by pressure. If we want to measure pulmonary compliance, we want to use the pressure required to overcome only elastic resources. So if there's no flow, P resistance equals 0. And therefore, transpulmonary pressure is entirely due to elastic pressure. So to measure pulmonary compliance, we want to measure volume and transpulmonary pressure at points of no flow. So traditionally we do this, for example, in the body box, all right? And so you ask somebody to take in a full inspiration, total lung capacity, and you occlude their airway and let them relax. So we now have a volume, and we can measure pressure there that since there's no flow, it represents only elastic pressure. All right, we'll let them exhale a little bit. We close the shutter again. We get a volume and a pressure, volume and pressure, volume and pressure, and so on. So this is the way that pulmonary compliance is actually measured if you want to measure an individual. So you might, depending on how long someone can hold their breath, get 4 or 5 points down this curve, which is enough to get an idea what this curve looks like. So we measure volume and P elastic during exhalation, so we need an esophageal balloon in place. We stop at 4 to 5 points to get both volume and elastic pressure. It's easiest done with a shutter stopping flow as in a body box, and it does require an esophageal esophageal balloon to measure pleural pressure. Static pulmonary compliance, okay, is change in volume over just this P elastic measurement. Dynamic pulmonary compliance is when somebody is actively breathing. So this is going to be change in volume over the sum of elastic pressure plus resistance pressure, or transpulmonary pressure during breathing. So we can do this, but dynamic compliance, I think you can see, is going to tend to be a little bit less than static compliance because you're adding this factor when you divide volume. Compliance of different lungs. So we can have people with restrictive lung disease, for example, which means they have to generate a lot of pressure to get a little bit of volume. These are stiff lungs, okay? Emphysema is an example where you don't have enough compliance, really, or sorry, you don't have enough elastic recoil, elastic tissue. And the compliance, again, is the slope of the line in each of these lines. So restrictive diseases in general have stiff lungs, decreased compliance. Emphysema actually has overly compliant lungs, and we'll talk next time about the importance of that or why that's a problem. Now, interesting observation. If we take a lung out of an individual or an animal and inflate the lung and measure volume, we're going to get what's called hysteresis. Okay, we're going to get an inspiratory limb which is very different than the expiratory limb. All right, a lot of space in here. If we repeat this experiment with the lungs completely filled with saline, the inspiratory limb and the expiratory limb are identical. What causes this difference between inspiration and expiration? Since it's not present in a completely fluid-filled lung, it must be due to properties of the air-liquid interface. Okay? That is surface tension. All right? And here's an example of surface tension being able to hold this insect up on a body of water. What is surface tension? Molecules in an air-liquid interface lack opposing molecules on the air side. So these intermolecular attractive forces are unbalanced across an air-liquid interface. So these forces tend to decrease the area of the interface. So this decreases in the lung, the internal surface of the lung, it actually causes collapse. And this is increased elastic recoil. So that's what surface tension is. Now there is a principle called Laplace's law, which says that if we have, for example, a structure with two spheres, but they're both connected to the same pressure source here, right? The difference in pressure between the airspace and the lining, right? So the airspace and lining depends on the surface tension, which can be measured, and the radius, or difference in pressure. The pressure required to keep this open is 2 times surface tension divided by radius. So what does that mean? It means that you have to have more pressure to keep a small alveolus open than you do a large alveolus. Now, if you're not able to generate different pressures here, right, this alveolus is going to open with less pressure. So what's going to happen is this small alveolus is going to collapse into this big one. Now, remember, the first episode, we talked about the fact that you don't want your lung to be one large hole or sphere. You want many, many spheres or alveoli to maximize the area available for gas exchange. So you don't want this to happen in lungs, all right? So fortunately, Mother Nature is kind to us and has created a substance called surfactant, which actually lines the walls of alveoli and reduces surface tension. Surfactant is made in these type 2 pneumocytes, stored in lamellar bodies, and is released in the alveolus to reduce surface tension. Now, basically, surfactant lines the alveolar surface of the lung, decreasing surface tension, produced by type 2 pneumocytes and stored in lamellar bodies. One component of this, dipalmitoyl phosphatidylcholine, is critical to the reduction in surface tension. Phosphatidylglycerol is critical to spreading of surfactant. The biochemistry here of these two substances primarily work to reduce surface tension or to spread surfactant around the alveoli. When you increase or decrease lung volume, you increase or decrease the concentration of surfactant on the surface of the alveolus. So let's say that this is the neutral lung volume, let's say FRC. So here there's a certain amount of surfactant on this alveolar surface. If you decrease lung volume, that is compress the lung, then this surfactant is compressed more. So what this means is that when you decrease lung volume, surface tension is decreased even more because surfactant is so closely packed. By Laplace's law, this small alveolus would collapse. So now it's got more of a decrease in surface tension to keep it open. When you inflate the lungs, surfactant is spread out further, right? And so what this does is surface tension is not quite decreased so much, but remember, the big alveolus by Laplace's law is going to stay open anyway, so it doesn't really need it. So this is just a beautiful design feature of the lung, that surfactant actually decreases surface tension more in small alveoli that need it to stay open than in larger alveoli that don't. Kind of looked at another way, surfactant molecules are more tightly packed in these small alveoli. The surface tension is lowest in small alveoli, and this keeps small alveoli and large alveoli open. The great equalizer here. So inflation, it turns out, spreads surfactant on the surface of the alveoli. With deflation, surfactant acts more effectively, thus increasing compliance. And this favors the maintenance of alveolar volume and closes collapse. So what happens is we're now going to inspire here, surfactant kind of spreads out, and so it maintains a higher lung volume even at a given pressure. So that this descending limb here is at a higher volume the whole way down, and the difference here is called hysteresis, and that's due to surface tension or properties of the air-liquid interface. There are two roles for elastic recoil in the lung, and probably in high school or junior high physiology classes, you learned that elastic recoil in the lung causes exhalation to be passive. That is, you actively take a deep breath and then you just relax, and these elastic tissues contract, causing exhalation. That is true. But in fact, the most important role of elastic recoil in the lung is to maintain the patency of intrapulmonary structures when lung volume is fixed. So if I ask you to take a deep breath and hold it, okay, now this end of the spring is fixed because you're holding lung volume. So this spring is now pulling on all of these structures, alveoli, airways, lymphatics, blood vessels, to keep them open. And the more elastic recoil there is, the more these stay open. Okay? And remember, at increased lung volume, there's more stretch on these, so these structures are even more open. Now, the other thing that happens is we've talked about alveoli here as if they were separate spheres, but that's not the case. They share walls with other alveoli. So, for example, this alveolus here, if it starts to collapse, this wall is being shared with this alveolus, this one with this one, etc. So that these alveoli will tend to oppose collapse of this alveoli and keep it open. So the geometric configuration of alveoli in the lungs is also responsible for maintaining lung volume or distensibility or compliance. So if we look at pulmonary compliance, there are three factors that contribute. One is elasticity or elastic tissue, and these are structural components, and this elastic tissue is in the walls of alveoli. Surface tension, probably the most important determinant, and clearly babies who are born prematurely, uh, certainly below 32, 34 weeks of gestation out of 40, have inadequate surfactant to keep their lungs open and require fairly significant treatment. And then pulmonary interdependence, which is the geometry of that terminal airspace. Variation in VQ is due to non-uniform distribution of ventilation. Distribution of ventilation is altered by airway obstruction or decreased sensibility. Compliance equals change in volume over change in pressure. And elasticity, surface tension, and pulmonary interdependence are all important at maintaining compliance. Decreased compliance is stiff lungs, small lung volumes, and is called restrictive lung disease. So next time, we'll deal with pulmonary mechanics part 2, and we'll be talking primarily about pulmonary resistance and then some aspects of distribution of ventilation as well. Thanks again to our director producer, Katie LeWinter. Thank you all for joining us in this, The Great Adventure.